Hey students, I thought making a video solution of the exam might be useful, and you can kind of go through and self-grade yourself and get an idea of where you are. And so by the time I get a chance to grade these, you can then, know what you did right and hopefully what you did wrong and learn from it and go forward. All right, so let's try this. Here we have the, I better grab some paper nearby here just in case. I think I'll need some calculations here. It says the radius of a hydrogen atom is 5.29 times 10 to the minus 11. What is the electrical force between the single proton and the single electron? So this is Coulomb's law, where we just learned, I think your author wrote it as a capital Q and a little q over r squared. But you multiply the charges, you divide by the distance squared, and Coulomb's constant. So in this case, we would have 9 times 10 to the ninth times the charge. And one's an electron, one's a proton. Those each have the same amount of charge. So I'll just put in their charge and square it. And, of course, the proton's in the center and the electron's orbiting around. And so their distance is the radius of the orbit. That's the 5.29 times 10 to the negative 11th, so I will square that. And it looks like I get 8.25 times 10 to the minus 8 newtons. So I guess the correct answer would be C on that one. 2 says, what is the correct image of the electric field from a dipole? And so I guess part of this is remembering, what is the meaning of a dipole? It's equal and opposite charge. So it looks like figure A, with the arrows pointing out, is the single charge, and it's a positive single charge. This would be a minus single charge, so it wouldn't be either of those. This then looks like we've got some kind of like charge, because I guess, right here, they would be pointing inward towards this one and inward towards that one. So this must be two negative charges. So this would be a bipole. So finally we get to the dipole, where this would be a negative and this would be a positive, because the field would point away from the positive and towards the negative. Here they're both pointing in, so they're both negative. This has got to be the equal and opposite. Same number of lines coming out. Anyways, so the correct answer here would be D. So there's number 2. Number 3 says a proton is released from rest between two charged plates. It has an electrical field strength of 300 newtons per coulomb, which I will remind you is the same as a volt per meter. That's going to be important here. When the proton moves a distance of 1.5 centimeters towards the negative plate, what is its speed? So using the principle of conservation of energy, we can say that the change in potential energy, and I'll just go magnitude, is equal to the change in the kinetic energy. And so it started from rest, and so 1/2 mv squared. And then this is the charge times the change in the potential, and the change in the potential, because it's a charged plate, is just the electric field times the distance. So there's a little bit of math here going on, but we can put all this in here. They say proton, so I guess I'll take the charge, 1.602 times 10 to the negative 19. Multiply it by the strength of the electric field, and I'll think of it as 300 volts per meter. So that when I multiply it by the number of meters it moves, 0.015, that would give me my volts, and my volt then is a joule per coulomb. So when I multiply by charge, that's my energy in joules. So this is the energy in joules. So that means if I put the mass in terms of kilograms, I would get a velocity in meters per second. So that's good. So I'll bring the 2 to the other side, multiply by 2. I will then divide by the mass of a proton, which is about 1.67 times 10 to the negative 27. That would give me velocity squared, so I will then take the square root of all of that, coming up with about, it looks like 29,400. So it looks like the answer would be A. Okay. Question 4. What is the resistance of a long wire? Okay, and so here is the resistivity and the length and the area, and so somewhere in here they give us the resistivity at room temperature. Okay, so there's the resistivity. They give me the length. It's 12 meters long. I guess I should look at the resistivity in units of ohms times meters. That's important because then when it says it's a 12 gauge wire, which has a diameter, so I need to cut that in half to get radius, the area would be pi times its radius squared. So half of 2 is 1, half of 6 is 3, half of 4 is 2, and that's millimeters. So putting it in meters would look something like that. Okay, so 1.72 times 10 to the negative 8 times a 12 divided by a pi and also divided by a 0.00132 squared is looking like maybe I should check my units here, but this would be meters squared and meters cancel. So we'll be in units of ohms, good. And 0.0378 looks like that one down there, D. So correct answer would be D. All right, moving along to number 5. Number 5 says, we've got a battery, shows a nice little picture of a battery. It's got an EMF. It looks like, I think that's the carbon zinc value you get when you react carbon and zinc. Internal resistance of 0.5, so I'll put a 0.5. It's connected to a load resistor of 2.25. How much power is delivered to the load resistor? All right, so there's a couple ways to do power. Maybe I'll focus my attention on I squared R. And I will then say, all right, I need to put in the resistance of the load, but I also need the current. Well, the current's then pretty easy to do because what we can do is notice that the current is in series, the load is in series with the resistance of the internal battery, of course, because that's the way the battery works. It just has some resistance. And so you are going to have these two in series. So that's the equivalent of the load plus the internal one. All right. So there is Ohm's law, and then there's the equivalent resistance. So the voltage is 1.54, and you add the two together, you get 2.75. So there's the current, 1.54 divided by 2.75 would give me the current. All right, now, so coming back to our earlier statement, if you take the current and you square it and you multiply by the load resistor, now the load resistor only, be careful here, notice I did add them together, of course, when I was trying to get the amount of current, because the amount of current has to flow through both of them. But when the question says the power just on the load, and if I would add them together and do the equivalent resistance here, then I would be getting the power on the equivalent of both of them together, not just the load by itself. So want to make sure I don't do the load by itself. Anyways, it looks like it's 0.706, so that would be answer B. Moving on to C, what's the equivalent resistance between these 2 points? Maybe the hard part is to kind of realize that between B and C, if there was any current, it would kind of have to go around this loop, and they would have to go to a 4K, a 4K, and a 4K would be in series. And so this is in series. And so then it might be easier to visualize, if you kind of redraw it, that this little outside loop is worth 12K, and this is worth 4K. And so now we've got parallel. So 1 over 12 plus 1 over 4 is 1 over the equivalent. So I'll go ahead and take my 12 and my reciprocal, add that to my 4 and my reciprocal, take the reciprocal of that, and we're looking at 3. So it would be a 3 kilo ohms. And I guess that would be answer D. Okay. All right. Question 7 says the picture shows the motion, that is the velocity, looks like it's pointing down, for an electron in a magnetic field, and we got dots coming out. What is the direction of the force? Well, this is that right-hand rule number 1. So you put your thumb in the direction that it is moving, and you put your fingers then in the direction of the magnetic field, and then the direction of a negative, and that's what we have, electron, yeah, is the back of the palm, and positive objects would go in the direction of the palm, negative objects would go in the opposite of the palm, and so that would be to the right. Okay. Number 8 says, what is the magnitude of the magnetic field at a center of a ring of currents 12.5 amps and a radius of 7.5 centimeters? Okay, well, here's the nice picture of it. But the equation I'm thinking of comes out of chapter 23. We used it, 22 is the test. And then we used it a lot in 23, and we just got done with the lecture. So hopefully kind of still focusing on it as we did the flux. But this is the equation for the magnitude of the magnetic field at the center. So this would be a 4 pi times 10 to the negative 7 for the permeability of free space. The current said 12.5 amps. So if I divide by 2 and also divide by the radius, which is the 7.5 centimeters, so I'll change it to meters, I get a field of 10 to the minus 4 here, about a 1.05 times 10 to the minus 4. Okay? So another calculation one. Here's more of a conceptual one. Magnetic fields are created from, and hopefully you heard me say many, many times, moving charges. And I'll continue to say that. I might change it a little bit because moving charges not only make magnetic fields, but moving charges make changing electrical fields, because like an electron makes both an electric field and a magnetic field when it's moving. I say that because we're now working in chapter 23, and in 23 you'll hear me say something like, hey, there's 2 ways to make a magnetic field. Then really it comes down to moving charges again. So you might even boil it down to just say one, it's moving charges, because moving charges is just what we call current, and that makes a magnetic field. But a moving charge, the charge also makes an electric field, and then when it moves, that electric field changes, and that changing electric field makes another magnetic field. So moving charges, again, are kind of the fundamental idea of what makes magnetism. All right, so finally the last one, question 10, or, the last multiple choice question, then we'll get to the free response. But the last one here, it says, what is the correct unit for electric potential? And that is volts. Okay, joule per second, that'd be a watt. This is a Faraday, this is an amp, so it's not any of those. All right, so let's try then number 11 here, and I'll call it 11OA. It says here, and got a little picture underneath there, a long straight wire carries a current of 18 amps, and it's flowing upward. An electron is traveling parallel to the wire, so here's a picture, in the same direction as the current, and the speed is 125,000 meters per second. If the electron is 15 centimeters, or put here in the diagram, 0.15 meters from the wire, what is the magnitude and the direction of the magnetic force? So, starting with the idea of a magnetic force, it would be QVB sine theta. So we need to know 4 parameters. We need to know the charge on the electron. That's the easy one, 1.602 times 10 to the minus 19 coulombs. We need to know the velocity, and that's pretty easy. That's given as 125,000. But maybe the two that are a little tricky here is we need to know the value of the field and we need to know the angle between it. We also need to know that direction, so to figure out, using the right-hand rule, the direction of the force. So we need to know the direction of the velocity, we need to know the direction of the field, and then finally we need to know the direction of the force. And that's what that right-hand rule number 1 was all about. All right, but why don't I just start with the magnitude of the magnetic field? Because that equation, we can kind of plug and chug into it and take the value of my current, 18 amps, the value of the permeability of free space, the 2 pi, which I will take advantage of and cancel off to a 2, and the distance away, or the radius of the circle, which represents the magnetic field at a given distance away, I'll put as 0.15. So, grabbing my calculator here, I'll go ahead and put in my 2 times 10 to the negative 7 for here, times the 18 divided by the 0.15, and it gives me 2.4 times 10 to the minus 8 Tesla. So there's the value of the magnetic field. And let me start putting these in. 1.602 times 10 to the minus 19, 125,000, and 2.4 times 10 to the minus 5. Let me put all the units together here on the edge. So the first one is units of coulombs. The next one is meters per second. The next one is a Tesla, which we can write as a Newton per coulomb per meter per second. So coulombs cancel and meters per second cancel, and we're going to left with newtons. Now, there is one other factor that needs some thought, and this is what we need to know to give us the direction, is we need to know the angle that is between the velocity and the magnetic field. So, coming back to our picture, we've got the velocity vector going up. So we know the direction of that one. The magnetic field I'll do in green. This is the one where we said it's right-hand rule number 2. Where we said go ahead and imagine grabbing the long straight wire with your thumb in the direction of the current, and the field will be in the direction of your fingers. So on this side of the wire, it looks like my fingers would be pointing out of the screen, and this way would be pointing inward towards the screen. So we've got up and we've got inward, and that's 90 degrees. So I can come back to my calculation and say the angle of orientation between the velocity and the magnetic field is 90 degrees. And sine of 90 is 1. So I won't even need to include it. I'll just now do my calculation. 1.602 times 10 to the negative 19. That's 125, 1, 2, 3, 3,000. Times 2.4 times 10 to the negative 5 for the current, and I get a force value of about 4.81 times 10 to the minus 19 newtons. So there's the magnitude of the force. Now, to finish off this problem, we got to get its direction. And like I said, we can get the direction using right-hand rule number 1. Of course, remember we had to do right-hand rule number 2 to get the velocity of the magnetic field. But using right-hand rule number 1, we would put our fingers in the direction of the velocity, so that would be up. Our thumb in the direction of the velocity, and our fingers would need to go into the screen. Okay. And then again, the direction of the force would be the negative, or the back of the palm there. And so this would be pushing, I guess I'd say this is to the right. Might be a good way to answer this one. All right, so there's the direction on the electron. It's to the right, which hopefully doesn't surprise. We did a homework problem and even an example problem like this, where if we had current in opposite directions, and we do. Remember, the electron's going up, but that's the equivalent of positives going down. So we have essentially over here current going down, and over here we have current going up. And we said something like that, the two wires would repel each other, and that's what we're seeing. So the electron is pushed to the right and has a magnitude of that much. So, yay! All right, so there's our first free response. All right, let's try number 11B. Okay, so it says, study the diagram below. Okay, so we've got these guys. What is the magnitude and the direction of the force on the 6 millicoulomb charge in the upper right-hand corner? Note, make use of symmetry or you might run out of time. Yeah, definitely make use of symmetry on this. Because conceptually, if you start working this one out, you're going to have something like this. You're going to say, all right, here is a positive 6 and a negative 6. So let me just focus on the force between this one that's in the upper right-hand corner, which we're asked to calculate. What is the magnitude and the direction of the force on the 6 millicoulomb charge in the upper right-hand corner? Okay. Now, here's where we can save ourselves some time, because if we look at this upper right-hand corner and this negative 6, we would see it would attract it, and those would be equal to each other in magnitude. Of course, one's horizontal and one's vertical. But if you imagine drawing a horizontal line and adding it to a vertical line, you're going to get something along the diagonal. Not only that, when you add them of the same length, so if you call that 1 and that 1, you might remember that the hypotenuse then is the square root of 2. And so we could take advantage of our symmetry by doing something like this. If we call this first one I was thinking about going down as force number 1, then what we could say is the combination of these two would be the square root of 2 times the force of number 1. See, that's what I mean by symmetry. We don't have to actually calculate the force between those two. Better than that, we know it's along the diagonal, because then this one in the corner is a positive, and so it would be pushing backwards along that same direction. And so they are actually in the same direction. And it's so nice to add vectors that are in the same direction, because you just add them like scalars. Things like a 3 and a 4 actually become a 7. Or a 3 and a negative 4 actually become a negative 1. You don't have to take the x component of this and then the x component of all of them and put all the x components together and then put all the y components together. That can be kind of tedious. But if you see a nice little symmetry here, you got that. So I'm going to say minus a little bit. So again, I only really need to calculate one force between the 6 and the negative 6. I don't even need to call it a negative 6. I just got to get that force, because that when I multiply by that square root of 2, I'm incorporating this other one. And then, like I said, if I can just figure out the force from this other one, I'm just going to subtract it, because they're in opposite directions. Perfect. And notice it too is a 6. So when I go to calculate it, it's going to have, something that has Coulomb's constant, charge 1, charge 2, and distance. In fact, the only thing different between this 6 and the one we're trying to find, the 6, so the two positive 6s, and this one here that I'm kind of focusing and calling F number 1, a positive 6 and the negative 6, is that we're further away. In fact, we're further away along the diagonal of a square, which we just said is the square root of 2. So if you had something that was the square root of 2 longer, it would be the square root of 2r, and you would multiply it by you would square it, and so you would get 2r squared. So in other words, down here in the denominator, when we go to calculate this force number 3, it's going to be just like number 1, except it's going to have a 1/2 in it. So I'll do that. I'll just say that the force coming from this positive 6 is actually what I will calculate for number 1 and then cut in half. Nice. I suppose I could even then factor out F1. But by giving this some thought and doing some symmetry arguments, all I really need to do is calculate the force of one of them and then multiply by a combination of their interaction, which would apparently be the square root of 2 minus 1/2. So let me actually then try the force between these two. And I'll put Coulomb's law on here for just that reason. And they're identical charges, so I'm going to cut Q squared. I'm not going to bother to say Q1 and Q2. So this would be 9 times 10 to the 9th times 6 milli, 10 to the minus 3. Yeah, milli. And then that squared. Then divided by the distance, looks like it's a 0.1 squared, enters. So it looks like this is the value of F1. So if I take that value of F1 and multiply it by the square root of 2 minus 1/2, I will get, looks like a 2.96 times 10 to the 1, 2, 3, 4, 5, 6, 7 newtons. Yay! And kind of along the diagonal. Yeah, I'll just use words here and say, yeah. Hopefully you say or write out diagonal or something to that effect. Because it says, how the question say it? Yeah, what is the force? So there's this magnitude, which is really kind of the main thing. But it also has a direction. And the direction, I guess I should keep this in mind when I start grading it. It's pretty obvious. I mean, if you're going to do something like this, you clearly know what the direction is. Because you're combining them in this appropriate way. All right, so finally, the last one here on the test, last one of the free response, it says, what is the current in each resistor? Kind of gives you a little help here and say, why don't you figure out what the equivalent is? And so coming to the picture, hopefully you kind of see that it would all come out here. But these two is where it would split and then recombine, and so there's nothing in between them. So you'd say these two are in parallel. And if you wanted to draw kind of an intermediate picture, then you might have something that looks like this, where you're saying this is the equivalent of number 2 and number 3. And then, of course, then hopefully when you see that, you'll see what I call the equivalence of the equivalent, because this would all be in series. The current would go into the first and then through this equivalent of 2 and 3 and then through there. So you're just going to add them together. And so I'll do a 20 here, a 20 here, and maybe I'll grab my calculator to figure out what this equivalent of 2 and 3 is. And since they're in parallel, I've got to do the reciprocal sum. So 30 reciprocal, 50 reciprocal, enter reciprocal is about 18 3/4. So 1875 newtons is what that's equivalent to. So I'll put that right here. And then recognizing that these are all in series, I would then add to it a 20 and another 20. And so you're looking at 58.75 for the equivalent resistance of the whole circuit. Which is really nice because looking at this with the equivalence of the equivalents, you could just go Ohm's law, which is 10 volts, divided by the equivalent resistance. And so I equals, in fact, maybe I should do it here. and say I equals 10 over this equivalent 50, what did I say, 58.75. And let's see, 10 divided by the 58.75 is 0.170. Or maybe you'd even say 170 milliamps. Okay, but anyways, we got, I would say, halfway through the problem now, because that is really for this circuit here, which is the equivalence of the equivalence. But what you're saying is what's coming out of this battery is 0.710. And if you translate that back into its equivalent, you're saying, again, that what comes out of the battery is this 0.170, and it would go through the 20. Here it would go through the equivalent of that, so we can talk more about that, but then it would go through that 20. And so finding the current in number 1 and number 4, you should be saying they are the same, and that is the 170 milliamps. So that's what we mean by the same. And that's what the hint is trying to say. It says make use of equivalent resistance, and hint, this will give you 2 of the 4. So we've already got the current in number 2 and number 4, but clearly it now splits off. Okay. And this is where the hint says go ahead and make a loop. And so maybe going down this part here, I will call this current number 2, and going down this piece, I will call current number 3. And so one of the pieces we know is that current number 2 and current number 3 must add up to our current, total current coming out of the battery, which goes through that first resistor. It also recombines after the resistors 2 and 3 in parallel. So either way you want to look at it, either of those 2 nodes, these nodes up here, either this top node or this bottom node, is the sum of the 2 current is the total, which we already have. And that's why we don't need to have a 3 equations, 3 unknowns type of problem like you might be doing in the lab. It's not that hard. It's only the 2 unknowns. So, of course, that means we need 2 equations. And so the hint of this said do a loop right here. All right, so if we start here and go with the current, now it would be a minus, since we're going with the current, and it would be the resistance of 30 times the current, which is 2. Then we would come around and go against the current, so it would be a plus. And then it would be its resistance, 50, and its current of number 3, and that has to equal 0. And so 50 times 3 is equal to 30 times 2. Or 5 times current 3 is equal to 3 times current 2. Okay. Now that can be helpful because somewhere in here I can do a substitution. Why don't I maybe solve this equation for number 3. So this would be 3/5 I2. And put it into here. So current number 2, I will leave alone. And current number 3, I'll replace it with 0.6 times current number 2. So that's 1.6 times current number 2. And now, putting that all together, I got 0.17 divided by 1.6. And we are at 0.106 amps for current number 2. All right, so we've got 3 of the 4 resistors now. The big piece is current in 1 and 2. That's the total, 170. Now we're at 106 milliamps. Which, of course, is where we could take advantage here of this equation. So if we take the total, and I'll just do in milliamps, so it's 170 milliamps, and subtract off the 106 milliamps, we're left with about 64 milliamps for current number, and this must be number 3, right? I put 3, okay. Yeah, current number 3. Okay, and that's it. That's the whole test. Hope it went well for you. Bye now.